Space optimized dynamic programming for longest common subsequence. In the last two lectures, we learned about longest common subsequence problem and the dynamic programming solution that can be used to solve this problem. In this lecture, we'll see how to bring the space complexity of dynamic programming solution down so that it becomes more space efficient. We learned that the time complexity of our algorithm is order of m into n. And what about the space complexity? Space complexity was also order of m into n because of the table, because of the dynamic programming table that we are using. In this lecture, we'll convert this table into an array and we'll see how to do the same thing in order of minimum of m or n. This is the time we are going to achieve. So let us see how this is possible. First thing is, whatever we studied in the last lecture, all those things are going to hold logically. The logic is the same. Whatever we did in the last lecture, everything is going to hold in this lecture. That is why I kept the algorithm as it is. I kept whatever we learned in the last lecture as it is. What we are going to do is, we'll make slight modifications on this algorithm here and there so that space optimization happens. That is, instead of the table, we'll convert this table into an array and use this array efficiently so that the same algorithm holds. This is what we are going to do. So what is the first step? First step is, you have these strings, same strings x and y. X is of the size m and y is of the size n. Everything is as it is. The difference is, instead of this dp table, create dp table, I am going to create array. This is the difference. So instead of the table, what am I going to do? I'll have two arrays. One array I'll call as previous array and the other array I'll call as current array. Why do I want two arrays? The reason is, if you look at this table, in order to fill any particular block in this table, what are you using? You will either use whatever is present in the block right above it, or you will use whatever is present in the block left to it, or you will use whatever is in the block diagonally above it. Only these three blocks are of significance while you are filling any particular block in this table. This also means any row which is at more than one row above the present row in consideration is not at all useful if you are filling this table. We filled this table because it looked logically right to fill the whole table, because you understood what each block is, what does it correspond to. But now that you know all these blocks are not required at all the times, and you know that only the row which is right on top of the present row is required for filling any single row. This means if you simply keep an array which will keep track of present row and the previous row, that should be good enough for you to execute the same algorithm. So this is the logic we are going to implement, because we know that the row just above the present row is the only useful row for consideration. Because of this reason, we'll keep these two rows in two arrays. Whatever is the previous row, we'll keep it in an array called previous. Whatever is the current row, we'll keep it in an array called current. This is what we are going to do. So let us see how to alter the algorithm accordingly. We already said we'll have two arrays. One array is called previous array and the other is called current array. So here this thing is insignificant now. We don't have complete matrix. We only have an array. Second step is, we said you have to fill first row and first column with zeros. This is also insignificant now, because whenever you are initializing these arrays, you can simply put all zeros, right? You can put all zeros in the arrays. You don't need any first row and first column to be zero now. Whenever you are using it, you will automatically keep filling the entries. Initially, make both the previous array and the current array as all zeros. What is the next step? Next step is, this is the crucial step in our algorithm. That is, whenever the values xi minus 1 and yj minus 1 match, what did you do? You tried to make it 1 plus diagonal element. And if it doesn't match, among the element on the left and the element on top, whichever is smaller, that is what you choose. So in order to rewrite this, first thing is you have to make sure that previously how were you iterating? You were iterating through the table. Row wise you were iterating through the table. To have the same effect, what are you going to do now? You are going to have an outer loop which will iterate through x. This is the outer loop. And what about the inner loop? The inner loop will iterate through y. So you will have two strings, and through the strings your loops will be iterating. See, the same thing is what we did in the last one. When you iterated through each row, that meant you took one string on the outer and one string on the inner and you iterated. But because it was a table, it looked beautiful. You were able to iterate row by row. This time, because you don't have a table, you have to imagine it. So you have to iterate through the strings. While you are iterating, whenever the characters match, that is xi minus 1, yj minus 1, whenever the characters match, what do you want to do? This time you don't have this matrix. So dpij is not there. Instead of that, you have an array current. So whenever you are updating your current array. So what should you do here? Instead of this, current of j, because it is an array, it has only one index, it should be 1 plus dp of I minus 1j. So whichever point you are standing, I minus 1 means one row up and j means same column. So what did you understand? You have to go one row up and in the same column, which means you have to go to the same index in the previous array. In order to fill the current array, you have to go to the previous array. Instead of dp I minus 1 j minus 1, you will write previous of j minus 1. So this should be previous of j minus 1. So this will do in case you are looking for diagonal. Okay, so here there is a slight mistake in what I said here. You are not taking the element right above dp of I minus 1 j minus 1. So you are taking diagonal element here. Initially it was dp of I minus 1 j minus 1. That is, we are taking the diagonal element and adding 1 to it. So how do you take diagonal element? Diagonal element means you have to go one row up and one column towards left. So one row up means instead of current array, you should look at the previous array. And one column left means for the jth index, you should look at the j minus 1th index. So you should go to the previous array because it is I minus 1. Because of that, you will go to previous array. And because the index is j minus 1, you will look into the j minus 1th index only. So current is equal to 1 plus previous of j minus 1. This is the updation. And what is the updation in case these do not match? In case xi minus 1 and yj minus 1 do not match, then what do? Maximum of dp I minus 1j. I minus 1j means I minus 1 means you are going one row up. J means you are staying in the same column. So what do? One row up means you have to see for the previous array. So instead of current, you are looking at previous array. What should be the index? Index should be j only. What is the next one? dp ij minus 1. Ij minus 1 means you are staying in the same row but you are moving one column to the left. So same row means you are looking at the current array only. So this should be current of, you are going one element to the left, j minus 1. So maximum of p of j, present of j, or current of j minus 1. This is your new algorithm. This one, you are having previous and current arrays, and instead of the previous matrix, you converted it into arrays. And what about this? Instead of dpmn, your final answer will be present in previous of n. This is the algorithm. So one more thing, we already told this is the algorithm. Let us just write a small pseudocode so that you'll be very clear on how it is implemented. So this is important. Whenever you want to convert it into an implementation, you want to actually write a code, you should be able to easily convert any algorithm and write the code. So for that, let us write it down. LCS, longest common subsequence of x and y. How do you find this out? Initially, you should know what is the length of x. Let us say m is equal to length of x and n is equal to length of y. Then what should you do? After this, you should know what is the previous and current arrays. So your previous, this is of length n. So you should have length n in this. And what about current? Current should also be having length of n. So these are your previous and current arrays. What is the next thing? You have to go through the loop. So it is for, let us say I is equal to 1 to m. That is, you are going through each of the element in your m. That m means your x string. What is your string? One is x, the other one is y. X is having a total length of m and y is having a total length of n. In this case, what are you going to do? You are going to iterate through x. While you are iterating through x, for each element, you have to iterate through y. So for j is equal to 1 to n. What should you do for 1 to n? You should, okay, let us refer this algorithm. I want you to be in alignment with the algorithm. So here, you have two cases here. First case is, in case both are equal, xi minus 1 equal to yj minus 1, then you are doing this. In case it is not equal, then you are doing this. So let us see both of these. In case they are equal, that is if x of I minus 1 is equal to y of j minus 1, then what will you do? In this case, your current array, current of j is equal to 1 plus previous of j minus 1. So this is same as taking the diagonal element. What is the other case? What is the else case? In case x and y are not equal, in that case, your current of j is equal to, what should you do? You should take maximum of, in case of matrix, you took the maximum of the top block and the left block. Here what should it be? Instead of the top block, you have previous of j, and instead of the left block, you have current of j. So this is the algorithm. Once you complete this, what should you do? You should finally return. What should you return? Here you should be returning previous of n. So one thing here is, here I simply considered n for the array. So in case the other string, that is your string x is smaller, what should you do? Simply interchange x and y. So whichever is the smallest string, that should be kept as y so that your algorithm runs faster. Or you can interchange the looping. So if you are looping the same way, make sure that whichever is your smallest string, that is your y. In that case, you will be using lesser space. And so the algorithm is clear by this point. One more thing is that, so what is the time and space complexity here? After this, we'll discuss a bit more of optimization. So time complexity here is same as the previous one. You are looping through m, then looping through n for each of those. So time is order of m into n. This is your time complexity. What about the space complexity? You are only having an array of length n. There are two arrays, both are of length n, which means your space complexity is order of n. So ideally, you should not write order of n. You should write order of minimum of m or n. Among m and n, whichever is minimum, that should be your space complexity, because you will form an array of the size of the smallest string. This is the logic. One more thing to be discussed here is there a possibility to use even lesser space? Here you are using two arrays.